Problem 3 is about improper integrals. What we want to do is we want to integrate 1 over x cubed plus x from 0 to 1. This is an improper integral because x cubed plus x is 0 at 0, so 1 over x cubed plus x has a singularity at 0. That is one type of improper integrals. The other type is if the limit, one of or both of the limits of the integration are infinity or minus infinity. How is this integral defined? It is technically defined as a limit, namely the limit for a goes to 0, integral from a to 1 over x cubed plus x dx. And we could solve it that way. However, to do so we would have to integrate 1 over x cubed plus x. We can certainly do this with partial fractions, but that's a lot of work. So to avoid these problems of partial fractions, we want to use the other method. We want to use a comparison test. What can we compare with? We have to compare with an integral which we know. Either we have to show that our integrand is bigger than something where we know that it diverges, or that it's smaller than something which it converges. So we first need to have a guess whether we want to show convergence or divergence. We also need to see what to compare with, and typically we would compare with what is called an integral over a pth power, 1 over x to the p dx. What can we tell about such an integral? If we have the integral from 0 to 1 over 1 over x to the p dx, this converges if and only if p is strictly smaller than 1. We've shown this in the lecture. So basically if we would have a square root or a higher order root in the denominator. On the other hand, we also know that the integral from 1 to infinity over 1 over x to the p dx, this converges if and only if p is bigger than 1. However, here we are in the case integrating from 0 to 1, so that's the situation. Now if you look at our integrand, yes, we don't have a pure power, we have x cubed plus x in the denominator. However, this doesn't look as if this behaves like something x to the p for p smaller than 1, so we will probably assume that we have an integral which diverges. Right, so we have established that our integral is diverging. Now we need to show that it diverges. So we want to use a comparison test, so we need to show that 1 over x cubed plus x is bigger than something. What do we want to compare it with? We could try to compare with 1 over x cubed, or we could try to compare with 1 over x. De facto, we know that polynomials for large values of x behave like the term with the largest exponent. For x towards 0, they behave like the term with the lowest exponent, so in this case they behave like x. So what we want to do is we want to compare 1 over x cubed plus x with 1 over x, and preferably we want to make it larger because we want to show that it diverges. Well, unfortunately this isn't larger than x. So let's actually look at the reciprocals. That's a little bit easier. If we look at x cubed plus x and we compare it with x. Well, certainly we know this is greater or equal than x in our interval between 0 and 1. That's not good. We would need this because that actually means that 1 over x cubed plus x is smaller or equal than 1 over x. That's the comparison which we cannot use. That's a comparison the wrong way around. So let's erase this. So how can we rescue this? Well, let's look at it term by term. Right, we need to make x cubed plus x smaller or equal than something else. Well, x is smaller or equal than x. This leaves me the x cubed. But on the interval between 0 and 1, x cubed is smaller or equal than x. So I could actually compare it with 2x. So x cubed plus x is smaller or equal than 2x. So 1 over x cubed plus x is bigger or equal than 1 over 2x. And this is a comparison which now works the right way. So this holds on the interval between 0 and 1. Right, now we can prove that it diverges. We know that the integral from 0 to 1 over 1 over 2x dx, this diverges. Namely, this is a p-series, right? 1 over x is a p-series. The factor 2 here is just a constant factor which doesn't affect convergence. So we have this integral diverges, and 1 over x cubed plus x is greater or equal than 1 over 2x. We can conclude that the integral from 0 to 1, 1 over x cubed plus x dx also diverges. And that is it. For part B, we have the same integrand, but now our integrating domain is from 1 to infinity. Again, we want to compare. However, now we are at x goes to infinity. If we look at this, 1 over x cubed plus x for large values of x basically behaves like 1 over x cubed. We know 1 over x cubed converges, so we should compare with 1 over x cubed, and we should show that it is smaller. Well, we know that x cubed plus x is bigger or equal than x cubed for x greater or equal than 1. So we can conclude that 1 over x cubed plus x is smaller or equal than 1 over x cubed. Why did we compare with x cubed this time and not with x? Well, we want to show convergence. We want to compare with an integral which converges, and the integral over 1 over x cubed from 1 to infinity converges, while the integral over 1 over x diverges. So that's why we picked the x cubed term. Well, so we have the integral from 1 to infinity over 1 over x cubed dx. This converges because it is a p-series. I can conclude that the integral from 1 to infinity over 1 over x cubed plus x also converges. And we've shown that this integral converges.